Okay, good afternoon, everybody. My name is Holger Kleinke. I'm the moderator of the next panel, which is Nano-based Energy Innovations, Breakthrough or Bust. I'm here on behalf of the Waterloo Institute for Nanotechnology, which is one of the other research institutes, likewise of the University of Waterloo, that actually was founded in 2008, so we just enjoyed our 10-year anniversary last year. WIN, as it's so lovingly called, consists of 96 faculty members and over 400 graduate students, and now we are also having over 20 research chairs. So with that, I'm going to introduce our first speaker for today, which is Zachary Cano. He's a PhD candidate from chemical engineering here at the University of Waterloo, came to us with a Master of Science from McMaster University. He is co-supervised by Dr. Zhongbei Chen and Michael Fowler. Zhongbei Chen is a Canada Research Chair in Advanced Materials for Clean Energy, very fitting for today, and Dr. Fowler works on clean production and distribution of hydrogen. With that, I give the floor to Zach. Please, go ahead.
Okay, thank you. So I'm here for presenting my supervisor, Dr. Chen's presentation. Okay, so this presentation is going to be on the future of electric vehicles, batteries, fuel cells, and how nanotechnology fits into those technologies. So I'll start off with an overview of those technologies, like a high-level overview, and then go into how nanotechnology can, or is already playing into these technologies. Okay, so as we know, like a big component of greenhouse gas reductions in the future will need to be from converting gas-powered vehicles to electric vehicles and fuel cell vehicles. So for instance, the EU, in the EU, Norway is planning to prohibit the sale of petrol and diesel vehicles by 2025. Automobile manufacturers are starting to announce that their vehicles will be replaced or have new versions that are with electric vehicles. And in the US, they also have plans to phase out fossil fuel power a little bit later than the EU, likely closer to 2045 or 2050. So looking at the global vehicle market right now, global car sales have actually started to flatline in the past few years. We don't know if that will continue, but if you look on the right side, the share of those vehicles which are electric are rapidly rising. So currently in 2018, that's 64% in total. That's year-over-year growth from the previous year. Now, this graph on the right side here looks at the current share of electric vehicles currently on the road today. Starting from 2010, like it's pretty much zero, but up to 2016, it's up to 0.2%. So it is starting to rise rapidly, but we have to keep in mind that in order to meet our greenhouse gas reduction goals for the entire world, the IEA has modeled that electric vehicle market must reach 86% market share by 2060. So we're still in the very, very early stages right now. So, so in order to continue having electric vehicles grow, we're going to need them to have better performance, lower cost, which the majority of consumers can use. Okay, so let's look at the current electric vehicle technologies today. So the first one, which was first introduced by Toyota, was the hybrid electric vehicle. So this is powered by both battery and oil. And there's also now starting to become, or in the last 5 years or so, plug-in versions of these vehicles. So you can charge them with electricity or put oil into them. And you can run from both sources. But the future of vehicles which will not be using oil at all, there's both pure battery technology and fuel cell power, which actually use a combination of batteries and fuel cells. So if we look at a technical comparison of the three typical vehicles of the representing those technologies. So the pure battery vehicle, this is the longest range, approximately is 460 kilometers right now, which is lower than gas-powered vehicles. But that's at a very high price as well. Most pure battery electric vehicles have a lower range than that, in order to be able to be sold at a more reasonable price. Plug-in electric vehicles, they have a lower price as well because they can get away with using a smaller battery because you have that gas power as the backup if you need it. So their range is comparable to what's pure gas-powered vehicles available now. And fuel cell vehicles as well. As I'll explain why in the next slide, they can also have a range that's comparable to the gas-powered vehicles today. So just a brief chemistry overview of the technical principles of batteries and fuel cells. So in this case, I'm looking at a lithium-ion battery, which is the dominant source of batteries in electrified vehicles today. So the way it works is you have a charge carrier between two electrodes in your battery, and that charge carrier is lithium ions in this case, and that travels back and forth between the anode and cathode, and then you have electrons going through your external circuit to power your motor. And for a fuel cell, you have hydrogen stored in your tank, and the hydrogen comes from that tank to the fuel cell, where it interacts with the electrolyte and oxygen on the other side, and that combines to produce electricity as well. So the lithium-ion battery, that reaction is reversible, so you can recharge the battery. Whereas the fuel cell, you need to have a source of hydrogen from somewhere in order to keep that, in order to get your range back after you've used the hydrogen. So what are the advantages of each technology and the disadvantages? So for fuel cells, the hydrogen fuel can be quickly refueled in minutes. So this is very comparable to our gas-powered vehicles today. You can just imagine that instead of a gas station, you'll have a hydrogen station. The disadvantages of fuel cells is that they have a high initial cost of acquisition. Currently right now. Fuel cells, as well as the hydrogen storage technology and hydrogen tanks, all require very high upfront investment. So that is a big reason why they're not very common today. So for lithium-ion batteries, the advantages is a lower cost of ownership and a lower cost of use. So while batteries are expensive, they are a lot more common today because there also have been introduced for some time for other technologies like our cell phones, cameras, etc. And they also are more energy efficient as well. So if you drive a lot of kilometers, you will likely be spending less money and using less power from the grid to charge the vehicle versus producing hydrogen to power your vehicle. The disadvantage of lithium-ion batteries, though, is that, like I mentioned, currently the range of electric vehicles which use batteries are relatively low compared to what we would expect from gas-powered vehicles today. And also there are some safety concerns as well, so you need to build a lot of external protection around the battery in the car, which takes up a lot of weight and further reduces your range. Okay, so there are advantages and disadvantages of both, and luckily these can be taken advantage of in different markets of vehicles. So for medium and short range and low cost of use applications, electric vehicles will likely be more dominant. But for fuel cells, because in order to get a longer range, you don't need to have more fuel cells. You just need to store more hydrogen in your vehicle. And hydrogen is relatively lightweight. So you can, as that red line indicates, to get a higher range, your marginal cost to get a higher range is much lower compared to electric vehicles. So that is the reason why they will likely be more dominant for long-range vehicles and and trucks as well, and also because they can be quickly refilled, high utilization vehicles as well. So like I said, this technology is still being developed now. So in terms of electric vehicles, the main driver is higher energy density and also longer life, lower cost, and higher safety if possible. For fuel cells, the main point again is lower cost and also higher durability to again last the lifetime of a vehicle. Okay, so now I'll get into the nanotechnology aspect of this presentation. So this is just a very high-level overview of Zhongwei Chen's research group work. So I don't have a excellent knowledge of all these topics, but if anyone's curious about anything, feel free to talk to me afterwards, and I can put you in contact with the right people. Okay, so in terms of lithium-ion batteries, they still can be further improved, and one of the most technical or commercially viable ways to improve the range of, or improve the energy density of lithium-ion batteries is to alloy silicon into the into the anode of the battery. So currently the batteries, the anode of lithium-ion batteries is mainly composed of graphite, but if we can add silicon into that composition, silicon has a higher capacity to store lithium ions. But there are some downsides to that, which are mainly due to the cycle life considerations. So there are many different solutions being worked on right now in terms of nanotechnology, such as coating graphite particles with silicon or multi-layer electrodes. And those just can help to buffer the downsides of the silicon and hopefully produce an optimal result. Okay, so lithium-sulfur batteries are a new type of battery. It still uses lithium ions, but on the cathode side of the battery, instead of metal oxide materials, which are typically used, we can use sulfur instead, which is very advantageous because it's much lower cost and it can store a higher capacity of lithium ions as well. But there are similar life cycle considerations for that as well. So right now, this technology is only very early beginning to be introduced into the market, and there's still much more improvements to be made. So the main consideration here in terms of chemistry is that sulfur, when it joins with lithium ions, it can produce soluble components, which will then leach into the electrolyte and cannot be recovered. And so a lot of the nanotechnology solutions are finding how to confine that sulfur or those sulfur components in order to keep it at the electrode structure, keep it at the electrode location, so that it will not lose its capacity over a number of cycles. Okay, and zinc-air batteries are a much different technology than the previous two ones I mentioned. So these they can also be other metals other than zinc, but in this case, for zinc air batteries, oxygen comes from the air and reacts with zinc. So oxygen is reduced on one side, similar to a fuel cell actually, but on the anode side, zinc gives up its electrons, and you can reverse this reaction to produce a rechargeable battery. So here in our group has demonstrated mainly on the air electrode side, materials which will allow you to both reduce oxygen during discharging the battery and then doing the oxygen evolution reaction, which you need to charge the battery, and finding materials which can do both of those things well enough with a high efficiency and a good cycle life. Okay, so in terms of fuel cells now, the main strategy for reducing the cost of fuel cell and improving the efficiency of them is to reduce the amount of platinum you need. So platinum is needed right now as a catalyst on the air electrode to reduce oxygen, to produce, or to be able to consume the electrons coming from the hydrogen. But platinum is one of the most expensive metals. So in order to reduce the amount of platinum, mainly you need to increase the surface area or increase the exposure of platinums to the oxygen, which requires nanotechnology solutions. And also, besides the platinum itself, another strategy is to tinker with the support for the platinum. So this lets you more evenly disperse the platinum and also lets you maintain the stability of the platinum as well to avoid it agglomerating, forming larger particles, which will then cause wasted platinum to be inside. Okay, so then there's more work as well on advanced support materials. Again, if anyone's curious about these things, feel free to talk to me afterwards, and I can put you in touch with the people working on these specific things. Okay, so as a high-level summary, high-performance batteries and fuel cells both require materials with maximized surface area and porosities. So nanomaterials and nanostructures are inevitable to meet this requirement. But the main thing to keep in mind when looking at the solutions to these technologies, if they can actually last a long time, so the lifetime of a vehicle in this case, and if the way you produce those nanostructures or nanoparticles is able to be manufactured at a high scale such that it can actually be produced at an affordable cost. Okay, so that's the end of the presentation. Thanks very much for your attention. I'll be happy to take questions.
Thank you, Zach. Like in the last panel, we postponed the questions until all speakers have given their presentation. Nice overview over alternative vehicles and how nanotechnology can help with the different types of batteries and fuel cells. Next up is then Shea, who is a graduate of the University of Toronto in electrical engineering, and he's a professional engineer. He started his career at IBM in electronics manufacturing and worked his way up to running the power systems group there. He was one of the founding executives of Celestica by becoming Celestica's chief technology officer. He then joined BlackBerry as senior vice president, and as a long-time advocate of clean energy, he then joined Arise Solar Technology here in Waterloo as CEO, and then is here as the CEO of QD Solar and co-founder of 3E Nano out of the University of Toronto, and 3E Nano has a booth in the back showing to us what they can do with specially coated windows. Dan, it's all yours.
Thank you, and good morning, everyone. Just a small note, driving here this morning and coming into the building, because I've done it many times, both with Arise and with BlackBerry, of course. You can actually see my office through that window just to the side here. So it's like old home week. Let me tell you a little bit about 3E Nano. And this diagram first is an interesting one because what we focus on is an optically clear film that rejects both solar energy and heat, so other forms of energy. And you're actually seeing a sheet right on this particular diagram here. And it's very hard to make out where the edges of the actual film are versus the colors in behind. But it gives you an idea just how optically clear and colorless our film is. And I'm going to talk a lot more about that. So what is 3E Nano? So it's a pre-revenue startup that was funded by the founders and some very, very interesting government sources, SDTC, OCE, and BIC. SDTC is a Sustainable Development Technology Canada, Ontario Centres of Excellence, and Bioindustrial Innovations Canada, all focused on clean energy. The technology is out of the University of Toronto, as was mentioned. It's a nano-thin film applied to various materials, namely glass and plastic, but others as well. It's designed to control both solar energy and heat from a radiation standpoint. The focus is on high visibility and high energy reflectance, so keep the heat out or keep the heat in, whether you're talking about summer or winter. Near color neutral and very large in terms of greenhouse gas reductions, and to some earlier presentations, a great way to reduce energy in a building. Because you'd be surprised that in downtown Toronto, office towers there cool their buildings 300 days a year. Yes, 300 days a year. So it gives you an idea just how much heat is generated and how important it is to reduce some of that load. So what is the problem we're trying to solve? Significant energy losses and heat gain, of course, from the sun. both in architectural and transportation industries, and condensation, snow, and ice in transportation. I'm not going to talk a lot about this, but an interesting part of our technology is one of the layer stacks in the film is silver, and that silver can conduct electricity, and when it conducts electricity, it heats up very, very quickly without breaking down. We can actually defrost a car windshield in less than 10 seconds, to give you an idea of what this technology can do. So when we talk about breakthrough or bust, we're betting on breakthrough when it comes to nanotechnology. And of course, GHG, greenhouse gas reduction's a real big one when it comes to energy reduction. So what is our solution? So it's a versatile nano-thin thin film, optically clear and tunable. And what I mean by tunable is when we change the thicknesses of our layer stacks, we can determine which part of the sun spectrum we're actually rejecting versus allowing through. So that makes it very interesting when you're talking about wanting to see the visible part of the sun spectrum, but wanting to reject the infrared part of the sun spectrum, where a lot of the heat is. And I'll talk more about that in a few minutes. It's electrically, when it's active, it's heatable. Highly abrasion resistance. The outside coating we put on it has a very hard coat, so it's very handleable and great in the outdoors. Low cost of material. This is a sputtering process, and when it's done in a roll-to-roll process, becomes very low cost. When I say low cost, I mean less than 50 cents a square foot. So it is down there. So again, from a nanotechnology standpoint, when people worry about high cost, this is not a high cost. This is a very low cost technology. Okay? And when it's applied to glass or flexible films, polymetric glass, fibers, cloth fabrics, you think fabric, why would you ever want to apply it to fabric? Well, in the case of a blind system or a curtain system, where you want to maintain the color, texture, or the artistic impression of what the original designer was trying to do, but you also want to reject the sun's energy, it's great to apply it to those materials as well. So who are the customers? Architectural, first of all, it's about a $1.6 billion business right now. This is basically coating windows, and the C3 group, by the way, that I've mentioned here, in terms of retrofit for architectural buildings, is located right here in Kitchener. So a local company, very large engineering group. Okay? And of course, Dynamic Facades, as I mentioned, Altex is a Canadian-based company out of Montreal. And PowerGrow, of course, is a US-based company in greenhouses, because this also applies to greenhouses. Greenhouses find that they're cooling the greenhouse through the summer, they're heating it through the winter. So if you can use solar control in both of those seasons, you can add a lot to the growing season. And to add a month to a growing season, as an example here in Canada, is huge to the greenhouse manufacturers. Next one is in transportation, so electric vehicles, example, Tesla. So if you have the ability to efficiently defrost or de-ice a window in an electric vehicle, at 1/10 the energy required to driving that battery through a heat source and then a blower onto the front windscreen, you'd be surprised at how interested the electric car folks are in this technology. Not to mention the fact that you can keep the heat in the vehicle by using low emissivity films, or keep the heat out so you don't have to use the air conditioner on an electric vehicle during the summer. So from a technology standpoint, the graph you see here, the one that looks a little bit like a rainbow, is what's called an AM 1.5. This is a representation of what the sun's energy does based on wavelength. So to the far left is UV. That's the harmful stuff that you don't like, whether you're out in the sun or you're having things discolored. This part in the center, the green part, is the visible. That's the part we all like. That's when we look out the window right now, what we see and enjoy. The reddy-orange part there is the IR part. It's the part that you may like in the winter when the sun is shining into your house, warming it up, but you don't like it in the summer because that's your air conditioning bill. So our job is to take both the red part and keep that out in the summertime, and the yellow part during the winter, that's heat. So that's the mid-IR portion of the spectrum. That's not generated by the sun. That's generated by the human body. It's generated by computers, by all things, including black body radiation. And our job is to keep that in during the winter months. So the whole idea that people don't realize, when heat enters or leaves a building, it does it in many ways. The traditional way you see is when the sun shines in through the window, you feel the heat of the sun just based on it radiating in. And when you are trying to keep your house warm during the winter, and you go up by the window and you have a double pane or a triple pane window, you say, okay, the heat is not conducting out. What most people don't realize, heat also radiates out through your window. So unless you have some form of coating, i.e. a low emissivity coating, heat is just going to continue to radiate out through that very, very expensive triple or quadruple pane window that you have full of argon or krypton. So coatings are very, very necessary to prevent the radiation part of heat exiting your house. So how does the technology work? Basically, we allow all of the sun's energy to hit the outside of the window. We take the IR portion of that spectrum, we reflect it back out, and we allow the visible part through, while at the same time keeping heat in the building, which is the orange part you see at the bottom. And what does that look like technically for some of the more technically driven folks in the audience? Well, this is a graph that's multiple versions. So the blue graphs you see there, okay, are all based on transmission, based on percentage. So that's how much light actually transmits through a window. So a regular piece of glass without any coating on it is about 92% efficient. And you may ask me why it's not 100% efficient, and that's some technical details due to Fresnel losses, but we won't get into that. But we start out at 92%, and then our job is to make sure we get as high as 82, 83, 84, 85% transmission. The red lines you see on the graph are basically reflectance. So how much of the sun's energy are we reflecting away with our coating? The yellow part, the little box that you see there, is the visible part. It's a part you want to see. It's a part you want to look out the window and enjoy nature with. Okay? The rest is heat, and it's the part that we don't want to have to deal with. So an example of what we can do, when I told you it's tunable, so on glass sample number 1 here, the visible light transmission, so the amount of visible, is 88% in this particular example. And the total solar energy rejection, so how much we're reflecting away, is 35%. And the same thing down, you can tune it the other way. Glass sample number 5 only has a visible light transmission of 50%, because this particular customer wanted to make sure that they rejected away almost 75% of the sun's energy. So it really depends on whether you want a tinted window or a perfectly clear window. We have the ability to do both, just changing the stack of our structure. And that's also not on glass, but also on polyethylene film, because we can do it on a flexible, very thin film. Same thing, ranging from 87% transmission and reflecting away 32%, right up to only 50% transmission, but reflecting away 65%. Management team is myself, Nicholas Kromanicki, who has been in IMAX, Siemens, a number of different optical-based companies. Dr. Nazir Karani, who's out of the University of Toronto. He's a tenured professor there. And of course, Gordon Jakubik. Gordon is our financial guy. Gordon used to be the CFO at Microsoft Canada, so a great guy to have in your back pocket when it comes to raising money and starting a business. So I said I would try and keep this thing under 10 minutes to get us back on schedule. Thank you very much.
Okay. Thank you, Dan, for this very nice presentation about 3D Nano and what you can do with your windows, keeping heat in and keeping heat out. Okay, so next up, we have Andy Sun coming to us from the University of Western Ontario. He's a professor at the Department of Mechanical and Materials Engineering and has a Canada Research Chair in development of nanomaterials for clean energy. So his research is in materials science and surface science in general, and particularly on nanotechnology and clean energy, where he works with carbon nanotubes and metal oxide nanowires as electrodes for fuel sensors, for fuel cells and sensors. Andy, floor is yours.
Okay, thank you very much for a detailed introduction. Good morning, everyone. I'm Andy from Western. Actually, I came Waterloo many times. So I gave a talk in engineering and also the nano program. But today I talked about something different. Previously I talked about the fuel cells, talked about existing batteries. But today I pick up the next generation battery for solid state. So today I think that is here, the previous speakers talk about both fuel cell and the batteries. Particularly, that is the first speaker, Dr. Cano, gave a very detailed introduction for comparison. I think now is I just pick up these solid-state batteries. For this part, let's start with recent news. So recently, some countries announced they will give up its petrol and diesel cars in certain years. So for example, here you can see the Norway and Netherlands. They plan to give up petrol and diesel cars by 2025. And also Germany and also Denmark is 2030. And the UK and France 2040, China is 2050. So let's say that here roughly for 20 or 30 years, the people try to give up. What is the alternative? So actually the two technologies are alternative. One is here talk about the battery-based EV cars. Another one is hydrogen-based fuel cells. So let's talk about what we are doing in my group, Western. So we dedicate the two devices. One is a fuel cell, one is a battery. And based on the materials and also characterization, particularly in situ characterization, synchrotron radiation, to understand what happened inside. So our study actually have a lot of collaboration with the industry, like Ballard Power Systems, General Motors, 3M, work on that from fundamental to practical. So basically here for battery study, we work on the electrode. Maybe I stand here is better. Yeah, here is better. So here you can see work on the electrode materials, the cathode, anode, and also work on interface. Dr. Shea also talked about coating. I will also mention the coating in batteries. So next generation batteries, for example, lithium sulfur, metal air. And also recent 3 years, we dedicate all solid state batteries. And also we work on the electric catalyst for fuel cells, particularly recent years focus on single item catalyst for fuel cells with Ballard Power Systems. So today I just focus on one, solid-state batteries. So in this part, I just gave an example how to address the problem in solid-state batteries, particularly the interface, and also new solid-state electrolyte. So let's see why we need to develop all solid-state batteries. So look at here is the motivation is two. One is a safety concern. Another one is a high energy density. So look at this one. We know Tesla is best EV cars all the world, but still have 2 accidents last year. 3 people died. So the reason here, we're still using existing flammable liquid electrolyte in the battery. So and also the cell phone, other things, a lot of accidents. So that's why we have a big concern, safety. So another one is Toyota have a roadmap. You see that talk about existing battery energy density. So here the limit roughly 300. If you want to double, you have to move all solid-state batteries. You can have 600 or even 800 the energy density and also the other type of battery. So that's why we see solid-state battery important for 2 things. One is the safety, one is a high energy density. So actually here is the key part in solid-state battery is a solid-state electrolyte. So here is, we should thank Japanese scientist, Dr. Cano. They developed a sulfide-based electrolyte. So it has an equivalent ionic conductivity with the liquid. So that's why he also developed different generations. So that's why it gave us the promise we can have a good solid-state battery. So look at the solid-state electrolyte, not only the one type sulfide, and also they have a polymer-based, oxide-based. But if you see all 3 of them, they have an advantage and also disadvantage. Even this one is sulfide, they have very high ionic conductivity, but they have other things, for example, chemical reactions with anode cathode. So we have to address all the things. So compared with the polymer, ionic conductivity is low, compared with the ceramic-based, is mechanical process is a problem. So that's why none of them can solve problem. The people see either have a hybrid or develop a new electrolyte. So our group work on 3 of them, and the hybrid, and also work on new type of solid-state electrolyte. So talk about the lithium batteries. They're actually very simple. The structure cathode anode electrolyte. So if you look at where is the big the concern actually at the interface. A lot of reactions at the interface. So that's why we need to address a problem at the interface. So this one is a liquid-based. When we move the solid-state battery, they have a more problem on the interface. For example, solid-state electrolyte with the cathode material, with the anode material, they have a more the challenge. What is detailed challenge? Actually 3. For example, talk about physical mismatch and also chemical reactions, or we call the space charge effect at the interface. So all 3 is very important control properties at the interface to have a better battery performance. So I don't think I have a detail the information for this part. I just gave an example. For example, talk about coating. Coating at the interface. What is ideal coating at the interface to address problem? So in the battery, we need the coating is ultra uniform, ultra thin, either on active material at the interface. So not only morphology, but also the properties. For example, talk about ionic conductivity, electronic conductivity, corrosion resistance, mechanical property, all the things at the interface. What technique can give us this kind of thin film? If you talk about many methods, CVD, PVD, SODO, all the method cannot give us ultra-thin nano-scale material. So for example, PVD, this on the top is very thick. Even the CVD and also the PVD only on the surface. Even the SODO, they cannot get ultra-uniform. Only the technique roughly now is the ALD process. We call atomic layer deposition. Or the new type we call molecular layer deposition. So the technique actually, here ALD, the general principle, we have a function group on the top, on the surface, and then after that introduce the material. They have a react with the function group. With the cycling, you have from mono layer to nano layer. So this one is for inorganic material. If we move organic material, the process we call molecular layer deposition. Still the similar thing, this one, you can have a hybrid to turn the property. For example, we talk about different properties. So our group using this one to address interface for the solid-state batteries. So we work on the sulfide, oxide, polymer, and the hybrid address interface problem, a solid state. Recently, we also developed a new type solid-state electrolyte. So this time, I just pick up 2 examples to see how use ALD, MLD address the interface problem. So for example, this first example, the PhD student using this technique to address the interface at the anode. This one is using lithium metal in solid-state battery. So they have problem because they have a lot of reactions. That's why we're using ALD, MLD to address it. So firstly, we want to compare in liquid-based electrolyte, how the interface, the coating can address problem. Because using ALD, MLD, you see the pink, compare that is no coating one. Coated one is very stable in liquid-based. And also recently we hybrid. Hybrid is much better because they have better toughness. So when we're using the same strategy, move to solid. So solid state, we pick up a solid state electrolyte. We're using that coating. We found the resistance much smaller. Particularly that here is very stable using that coating compared without coating. And also you have a full cell battery. You test it. You found without coating, just run 30 cycles died. but with the coating, you can have a good performance. So this one with the anode part, this is the cathode. If you see the cathode, they also have problem. So we're still using the coating. So the coating here, Toyota using that is ALD coating on this one. But we found not only the first coating important, second coating also important. For example, the yellow one is a solid-state electrolyte. We need this kind of shape in the battery. So with this idea, we compare three. For example, using ALD, you have a coating on the lithium cobalt oxide. The electro process also important. If the mixture mechanical method is not uniform, using chemical one, very uniform. So finally, we found is this one without coating, you see that is no capacity. With that one layer coating, not uniform, is not that good cycling performance. With the two layer coating, really good performance for solid state. So also we compare with the liquid. You see the liquid and solid totally overlap. So that means we can get that good performance. So after this one, I'm just using a few minutes to show you our recent new results. New type solid-state electrolyte. We call the highlight-based solid-state electrolyte. So Panasonic just reported last December. They found one type, the solid-state electrolyte. So it's with a very high ionic conductivity. And also that is very good performance for solid state. With the cathode is quite stable too. So we also work on that system, highlight based. So recently we found a higher ionic conductivity. The lithium indium chloride is very high ionic conductivity and also very stable in the environment. Because sulfide you cannot handle in the air, they have a reaction. But this one you can handle in the air. So it's with this kind of the electrolyte compared with the sulfide is very stable. So this method we're using ball milling, but we try to see scale up for industry application. So actually that is last week we just report using the liquid based the method, we can have this kind of electrolyte. So also very high ionic conductivity. A more important thing is here is we put this solid-state electrolyte in the water after heating, we can have the same performance. So that means really stable. And also we can have a mass production. For example, kilogram you can synthesize. So performance, you can see that the battery performance is really stable. So that means we can use this new type of solid-state electrolyte, replace other types. So talk about this highlight-based solid-state electrolyte, and then compare with the promoting one sulfide. You can see that many different properties. The before last year, the yellow one, is this type of electrolyte is very poor performance. Many things. But until that is the this year, the green one, suddenly it's improved a lot. But still here is, you see the one challenge is with the anode. So that means other properties, ionic conductivity and the cathode, air stability, all things addressed. And also with the all study, this one is compare sulfide. If you compare sulfide-based electrolyte, you can see the green one is much better than red one. So that means that in this type is very promising for solid-state batteries. So let's have a summary. Actually, I just gave you a few examples to see solid-state the battery important. And also they still have a lot of problems. How to using nanotechnology address the challenge in the solid-state battery. We talk about the ALD, MLD technique to address anode, cathode, and also we developed a new type solid-state electrolyte. Also, that's my group members, and also we have collaborators with the Bala Power System, General Motors, 3M, with China, and also SPI company. That's former members. Particularly, I want to point out 3 students from Waterloo all the working in company now. And also I'm looking for new student, new postdoc fellows. So thank you very much for your attention.
Thank you, Andy, for another nice examples of how nanotechnology can help us with clean energy. So far no busts yet in this panel. Next up is Samaneh Shahgaldi, who is research associate here at the Energy Research Center of University of Waterloo. She received her BSc and MSc in chemistry, actually, and the PhD in chemical engineering in 2013, and has worked at the Hydrogen Research Institute at the University du Quebec, and received Hydro-Quebec Awards for 2 years. Research work now is focused on synthesis and characterization of novel nanomaterials and polymers for hydrogen storage and fuel cells. Samaneh, please, the floor is yours.
So, hello everyone. Today I'm here to presenting our group on behalf of Dr. Shahgaldi. So today I'm going to talk about engineering advanced MEA from material to microstructure, design, component, almost everything in membrane electrode assembly. Before that, I want to let you know that we are located in Energy Research Center, University of Waterloo, in the 3rd floor, and we are working on different projects like battery, spray, combustion, and PEM fuel cell. That today I'm going to focus on PEM fuel cell. So today we hear a lot about the proton exchange membrane fuel cell, how does it work, and what is the chemistry behind that. So in brief, it's an electrochemical device that converts electrochemical reaction to the electrical energy. It means that we can get to produce electrical power from the electrochemical reaction. So we have hydrogen as a fuel and oxygen as an oxidant. And the byproduct is a water 100 times or much higher, cleaner than tap water that we have. There are a lot of advantages like environmental friendly, direct energy conversion, high efficiency, and low operating temperature. But still, for mass production and commercialization, there are problems like durability, performance, and cost. So all these 3 issues are interconnected and related to the membrane electrode assembly. But what is the membrane electrode assembly? Actually, I brought one to show you, and if you're interested later, you can come and see it over there. So all the things in fuel cell happen in these thin layers, less than 500 micron, okay? So what we have here, we have a membrane, catalyst layer, and gas diffusion layer. In the catalyst layer, we have a catalyst, of course, that the best one so far is platinum. We have carbon as a support, and the ionomer, that each of those plays an important role in the performance and durability of MEA. So what we want to do, we are ambition to do to develop our MEA through the design, component, because all the parameters are trade-off with each other. For example, if we have a high activity in the catalyst, it's not guaranteed that we get a good performance in the fuel cell. And we need to understand between the transport impact and the activity of the catalyst. Or at the end, we need to develop MEA with the low cost, high durability, and reliability. So far, we have 3 main methods, and recently they add another 4th method for producing membrane electrode assembly that is classified based on where we put the catalyst. The first one is catalyst-coated substrate, that we directly deposit the catalyst on the substrate or gas diffusion layer. The second one is the catalyst-coated membrane, that we deposit the catalyst directly on the membrane. Or the other is decal transfer method, that we have an inert substrate that we transfer the catalyst through an inert substrate to our electrolyte or membrane. And recently they announced a new method, DMD, or direct membrane deposition, that just works for the small size of MEA, because if we go to the industrial size or bigger size of MEA, we have the leaking problem. So for now, we are focusing on the 3 main methods. So this is some result that I want to share with you. We found that no matter what we are using, what kind of method we are using, with little bit modification of each, we can reach the maximum power density if we have high platinum loading. I mean, if we have enough catalyst to react in our reaction, okay? But if you go through the literature, you will find a lot of discrepancies on the result. And we found that these discrepancies comes from the amount of the platinum or catalyst the people they're using. So that's why some group says this method is better, the other goes with the CCS or CCM method. We found if we bring down the platinum loading to 0.125, we will find out that the CCS method, for example, here, shows the lowest performance. However, in the same condition, when we have high platinum loading, we will get the exact same performance. Besides the MEA manufacturing method, we did a lot of work on the microporous layer. Microporous layer is a layer on top of the GDL that it acts as a support for our catalyst layer. And it helps us to remove the water from our MEA, and it helps to the thermal and electrical conductivity. So we did a lot of research on new material like graphene, volcane, high surface area carbon. We made a lot of microporous layer for our fuel cell. And we found out the graphene with the optimized thickness and electrical conductivity shows a very good result as a microporous layer, and it increased the durability, and it's really resistant to corrosion, carbon corrosion. Not only the microporous layer, but also we did a lot of work on commercial catalysts, like platinum carbon. We have different kinds of platinum carbon with different ratio of platinum to carbon. If we go through the literature, we will find out there are a lot of research on the half-cell result, like ex situ experimental result. So if we compare these two catalysts together, we will find out the active surface area of the catalyst, for example, it's comparing between 43 to 62. So we expect the higher activity of the catalyst end up to the better fuel cell performance. However, when we make the fuel cell, we will find out the result is vice versa. So that's why we need to think about all parameters when we want to develop and design an MEA. So that's why we need to think about, okay, what is the diffusivity resistance? What is the permeability? How all these parameters come to account. Besides the role of the catalyst and NPL, also the other component that we have in the catalyst layer is ionomer. That ionomer has two roles. One is the ionic conductivity and act as a binder. We find out that different ionomer and different ratio of the ionomer have the substantial impact on our MEA performance. For example, here we compared the Nafion with the equivalent weight of 1,100 with the other almost same structure with the name of short side chain with the lower equivalent weight of 800. So we find out with a little bit change, the difference gonna be huge in terms of performance and durability. Not only the type and the ratio of ionomer are important, but also the design also important. So we made a design in order to save the ionomer. You know, we made 9 case studies of single cell and tested on different design. For example, how much ionomer we need near the membrane, how much ionomer we need out far of the membrane in order to have a better performance. So we find out we can decrease the ionomer amount by 10%, and still we have the same performance when still we have the same performance in our fuel cell. We put all these things together for optimization. We develop an MEA that is not sensitive to flow of reactant. That is really important. It means that if we have high flow of hydrogen and oxygen, or if we have low flow of hydrogen and oxygen, we can get the same performance. Besides this, we recently also received a project to synthesize the platinum carbon from the raw material. Here, for example, we produced the cubic shape of platinum. These cube shapes are platinum, and the other shows the carbon as a substrate. So while we are playing with the shape, we want to increase the surface area. We don't want to produce the spherical shape of the platinum. We want to have the higher surface area shape, plus we have a better connection with the support. Then we bring down the size, okay, in 2 nanometer and 5 nanometer in order to increase the activity. As you see that we produced this recently, and we have a really good dispersion and good performance and durability. So this one I want to show you. The black graph shows the performance of one of the best MEA available in the market from one of the reputable company. And the red graph is the one that we produce in our lab. So in summary, we found that each part and component and design have the substantial impact on an MEA performance and durability. And I'm really happy to announce that we are really, really near to hit the 2020 DOE target in our lab. And our ambition is that we go further and optimize each component design and increase the performance and durability. And these are that company that sponsored our project. And thank you so much for your attention.
Thank you, Samaneh, for another demonstration of a breakthrough in nanotechnology. Now is the time for questions to any or all of the panelists, if you please.
Converting, everybody's probably familiar with oxygen and hydrogen combining the water. So splitting that, I know it requires a little bit of energy, but there's been some work in the history in the past that developed that strategies, and some of them were mysteriously gone. So I'm just wondering if there's any work done, with the membrane technology and the batteries, utilizing that technology for the water.
For the water?
Water, yes, as a source.
Water electrolysis?
As a source of energy.
Yeah, there are a lot of work on water electrolysis. I'm not sure if I got your question correctly.
Okay, never mind.
Did you have any idea, Dr. Song?
Basically, water-based cars. There was a lot of
water-based car, yeah.
Exactly. So using just basically pour water in the car and drive it.
I saw some research, but I don't have any information that I want.
This question is for all panelists, and maybe not so much for the 3N, because it's a different question I have for that.
So I guess the question is, are you familiar with research done on water-based cars? So engine that could run on water, right? So anybody who would like to answer this question?
Let me try. I think that idea, yeah, people try to using water split to generate hydrogen and then use it in fuel cell directly. But people have this concept, but I don't think it's very good progress. Just see now the water split, very hard research to see generate hydrogen. But directly using this still need a time. Demonstration not ready.
I was just hoping that maybe through the progress of nanotechnology, there may be some breakthroughs, or there may be some new information, finding out why from biochemistry, water is the anomaly in the world, right? So there's something about it that could potentially be discovered at a nano level. So that's why I'm bringing this up. Speaking of the cars, plus speaking of the water, it's just, you know, plenty of it around. So that's all.
Yeah.
I find it appropriate question.
For sure, that's a very important area, the hydrogen from water. Yeah.
Okay, is there anything else? There's one question on the left.
Thank you for the great presentation. I just have a quick question. As you mentioned, like our car industry is going forward either electric vehicle and also like fuel cell, a hydrogen-based vehicle. Do you see a future? So my question is that do you see the future where we converge into the one of those technology? For example, like either we're going to be using electric vehicle or hydrogen fuel cell vehicle, or do you see a future where we rely on both type of energy sources? Yeah.
If I could, like I believe it would be both technologies because they have different advantages. So for hydrogen-based technologies, because hydrogen is a lot lighter material than any battery, they tend to be better for longer range vehicles and also trucks as well, because they can take up less volume of space, whereas a battery will take up a large amount of the space that you'd be needing to transport other materials. So for trucks and long-range vehicles, I think hydrogen, most people that I've seen talk about this say that hydrogen is the best for that technology, whereas the shorter range vehicles would be battery-based. So I think in order to meet like greenhouse gas reduction goals, it's best to be able to use both technologies.
Thank you.
I can have comments on this one. I think I agree with Dr. Cano. See, that is we cannot see which one replace another one. I think the parallel for these two technologies, particularly a lower range and a higher range, may be different. Particularly the timing, the battery-based electric vehicles is available even now or near future. But for hydrogen fuel cells, still need some time, particularly the cost. So here is, in the future, I think both together can meet requirements.
And I add something that the research is going very fast. A couple of years ago, we used 8 milligram per centimeter square platinum in our MEA, and we are using now 0.125 to get the same performance.
Do you think those technologies can be used in the aircrafts as well?
Yes.
Hydrogen fuel cell aircraft, do you think that's something that's possible in the future?
Yes, small the plan now is no people, no pilot that one, is now using both. I think that is step by step.
Okay, thank you.
Okay, in the interest of time, we should move on and enjoy our lunch. And during the lunch, we will get another presentation by the Executive Director of WISE. Let's thank the panelists once more.